Bon, bonjour, on va commencer. C'est un très grand plaisir aujourd'hui d'accueillir Mike Montgomery. C'est un pilier de la communauté des ouragans et cyclones. Et il fait ses travaux à travers les problématiques théoriques et aussi de la prévision des ouragans. Ça tombe très bien aujourd'hui aussi parce que il y a sur la première page des nouvelles, ce nouveau ouragan Beryl qui dépasse toutes les attentes. Donc Mike, il vient de Seattle originalement. Il a fait ses études en mathématiques à Seattle, ensuite il a parti à Boston, à Harvard pour faire sa thèse sur les systèmes frontaux dans l'atmosphère. Ensuite, après la thèse, il s'est intéressé aux ouragans et il a travaillé à NOAA en Floride. Ensuite, à l'Université de Colorado. Et maintenant, depuis 2006, je pense, il est à Monterey, Naval Postgraduate School. Donc, il est chez nous pendant 3 jours. Donc, si vous voulez discuter avec Mike après, c'est un peu chargé cet après-midi. Demain, on part à Météo France. Et jeudi, c'est grand ouvert. Donc, si vous voulez parler avec Mike, fais-moi signe, je te mets sur la liste. Mais maintenant, je passe la parole à Mike. Mike, your turn. You can tell us all about hurricanes and rotating convection paradigm.
Merci beaucoup, Monsieur Nicholas Paul. I wanted to say thank you very much. It's nice to be here. It's very nice to be to learn about the institute here, the laboratory. It's nice to see a good crowd. I don't know a lot of French, though I'm supposed to have learned it in high school. So I know un petit peu parler français, but anyway, I'm not going to give my talk in French. So this work is in collaboration with Roger Smith, who is Professor Emeritus now at Munich, and we're working closely. We just finished writing a textbook. Talk about that a little later, and some of our collaborators, Gerard Kilroy, John Persing, and this is a picture of Roger and I. I see some really nice pictures here in the room. These are pictures of us in Canada. We were working, we went to a workshop that Andy Maida had organized in Banff. It was really nice, actually. So even if you study tropical cyclone, you don't have to study tropical cyclone in the tropics. You can study sometimes in the mountains. Just as astrophysicists don't have to travel to Alpha Centauri or the Andromeda Galaxy to study astrophysics, we can study tropical cyclone in different places. So I'm doing that now as I'm traveling through Europe. I'm enjoying it very much. It's nice to be away from the United States for a little while. Okay? It's a little crazy right now. Okay. So let me just say that the tropical cyclone, just to give a little orientation, this is from Holton's nice book. After his pictures after Gary Emanuel's schematic, but basically the big picture of the tropical cyclone, just to get everybody familiar, tropical cyclones are large-scale geophysical vortices in the atmosphere that form in the tropical sector of the atmospheric circulation. They tend to be, once they form and become mature, they tend to be fairly large scale. At least this picture doesn't have a scale on it on purpose, but it could be 1,000 kilometers across horizontally and maybe 15, 16 kilometers deep. So they tend to be broad and shallow vortices. The circulation is, the primary circulation is it's the circulation that would be into and out of the bore. And that's not depicted in the schematic, but the overturning circulation is the one that's depicted in the schematic. The primary overturning circulation is coming in the shallow boundary layer of the tropical cyclone, though there's also some circulation that comes in above the boundary layer. We'll talk about that a little later. That's very important for spinning up a tropical cyclone. And this air that's basically coming in is picking up moisture from the underlying ocean. It's evaporating water. The water that is evaporated is in a form of water vapor, so the energy is in latent form. So it's latent, it's intrinsic to the air, ready to be released when the air is lifted in cloud. When it's lifted above the boundary layer to become cooler, then it saturates, becomes foggy, becomes cloud, there's little liquid drops. And if the updrafts are relatively strong, those liquid drops coalesce, and the liquid drops then start to precipitate into little raindrops, and it starts to rain. Now, of course, tropical cyclones have a tremendous amount of rainfall. The precipitation that falls from tropical cyclones can be very devastating in different parts of the world. And this circulation extends to the upper troposphere. In the tropics, it's around 15 kilometers. This circulation in the interior region, these cumulus clouds, these deep cumulus clouds that form in the outer region don't extend as high generally, and the ones far out kind of look like trade convection, trade cumulus. Now, if you take a step back and look at this picture, you would say, oh, that picture also looks like the tropical circulation. If I just kind of don't worry about the asymmetry between the northern hemisphere and the southern hemisphere. The air is warm in the tropics, and it rises warm and moist, and it rises in the tropics, let's say near the equator, and then that air, say in the southern hemisphere, moves poleward, and that basically transports that heat from the tropics towards the pole. So it kind of looks like the Hadley circulation in the tropics. So the hurricane is a small scale version, essentially, of the Hadley circulation in the tropics. Okay? In this case, there would be the summer hemisphere and the winter hemisphere. Those are details. Little detail here in this region inside. Region 5 is the eye. That's the region where the air basically is slowly subsiding, and it's relatively, it's cloud free, so you can see down into the center from satellite pictures. And when you fly through hurricanes, once they're mature, you may fly through them at say 10,000 feet, 3,000 meters. And when you fly through, you punch through this, the most intense, the most vigorous organized convection. Typically it forms in almost a ring around the center. You fly through and it's basically cloud free. And it's this big Colosseum. It's like a huge Roman Colosseum where clouds are basically sloping outward, and you see stratocumulus in the center. Okay, so that's just an orient to you on what tropical cyclones are. It doesn't explain to you, of course, how they form, how they spin up, and how they decay. Now, I'm going to just give a few examples. I'm going to go through these kind of quickly because I want to try to stay, if I can, I want to stay on time. I've been told that you're very strict on time, and I don't want to be pulled off stage. So here's an example of some of the problems we face in meteorology and fluid dynamics and theoretical physics. In forecasting hurricanes, this is our storm that formed in 2020. This is a time period, it's about a 2-week time period. The storm kind of became a disturbance the forecasters were tracking, and it went through a very rapid intensification. It made landfall in Nicaragua, caused tremendous rainfall and flooding, loss of life, unfortunately. Then it moved into the Gulf of Honduras, went over Cuba, and came down into the Gulf of Mexico and went over across Florida. Pretty much hit a lot of the populated areas. And this storm formed during the time many of us were still locked down because of COVID. Some of us were teaching classes, researching. Maybe we had to research at home. We couldn't come into work. And 2020 was a very lively season. It was at the end of the season, it picked up and it became a very active season primarily because storms were forming in the late season in the Caribbean region, where the sea surface temperatures were relatively warm. And the vertical shear, which I won't get into details, but it was relatively favorable, and the MJO, the Madden-Julian oscillation, also in a somewhat favorable phase for this part of the world. So this temperature is around 30 degrees, and this is like a big bathtub. Everybody likes to take baths, or you have kids that take baths. They love water about that temperature. Nice temperature, okay? And it's a little bit too warm for swimming laps. I do a lot of lap swimming. A little bit too warm for competition. The Olympic swimmers will not be swimming in 30-degree water. They'll be swimming in maybe 24, 25-degree water this summer. But this is a very favorable condition. And we can see on November 1st, this is what the forecasters were looking at. This is in the visible. You can see the cloud fields kind of starting to organize, kind of looks like a spiral galaxy, but on obviously a much smaller scale. But, there's a lot of clouds that's kind of swirling around the center, but it's not necessarily really, really strong. Forecasters saw this, and they looked at some data they had available, and they issued a forecast for a moderate a tropical Category 1 hurricane in 2 days. So when it was at this point, it was somewhere around here, and they issued a forecast that it would be a Category 1. It was tropical storm at the time in 2 days. Okay, in 2 days, it had formed rapidly, and it became what we call a pinhole storm, where there's a pinhole eye, and you can kind of expect that when you have a pinhole, the air is converging down to a very small distance, and the air is spinning around very fast. It's like the ice skaters during the Winter Olympics. When they bring their arms in, they spin a lot faster. So that's what happened for this Hurricane Eta, and it became a Category 4 tropical cyclone. It was not forecast. This is just an example of this is what forecasters were looking at. It was a tropical storm, storm force winds, and it had about that distance to traverse. About 600 kilometers, maybe something like that. And basically, this is the forecast, various models. I won't go into details. The official forecast, the forecast that the forecasters put out for this portion of the world is here. It's called OFCI, Official Intensity Forecast. So it's kind of in between the envelope of the model estimates. Some are statistical, most are deterministic. So they run models, they're solving Newton's equations. These models at that time were not AI models. I know the AI people have gotten involved in this. They're doing some interesting things, but I won't get into that. They may make good progress on some things, but I still put my money on the deterministic models. Okay. However, the official forecast is here, so the official forecast is Cat 1 within about 2 days, as I said. But what happened? Use the pointer, Mike. There you go. What happened is the hurricane organized very quickly, and it became a Category 4 storm. Now, this is not something you want to see happen if you're a forecaster, because it's what we in the community, many of us refer to as a forecaster's nightmare. Because if you're a forecaster, you don't want people in Nicaragua or Honduras to wake up within 36 hours and be told that you have a Category 4 hurricane just off the coast, and it's going to be devastating in terms of rainfall and wind and tremendous damage in the communities. They don't have the same infrastructure that we have in the United States or in France or other parts of the developed world. So when it starts raining, it really rains, and that water can be very, very damaging. So that forecaster's nightmare is basically not something we want to have happen. We had another incident like this happen in last year in a storm that hit Acapulco. It's called Hurricane Otis. And it was basically a category, I think the forecasters were forecasting a Category 1 or Category 2. They didn't have reconnaissance airplanes in at the time they made the forecast, and it had spun up to a Category 5. So hurricanes there's a span of intensity categories from 1 to 5. 5 is basically devastating. 3 is very strong and very destructive. 1 is, sustained winds of 100 kilometers an hour. 110 kilometers an hour, kind of what you on the freeway, typically 110, close to that. Category 5 can be sustained winds of 150 miles per hour. That would be like 200, I don't know what, I have to do the conversions, like 240, 230 kilometers an hour, something like that, okay? So much more devastating. And this is the category 4, okay? Okay. So here's an example that just happened. And the tropical Atlantic right now is fairly warm, very warm. It kind of looks like, in many ways, at least the lower part, the tropical Atlantic looks a lot like this. The SSTs are pretty warm through a big chunk of the tropical Atlantic. So I think they're unusually warm, maybe half 1 degree warmer than the climatology. So I'm not going to say whether that's global warming or whatever it is, it may be contributing to it, but it's definitely warm. So that sets up conditions that allow disturbances in favorable environments with relatively weak vertical wind shear. That sets up conditions that support the formation and intensification of storms. Now, in this case, tropical cyclone Beryl, on Friday night, or I guess early Saturday morning, this was the forecast. Tropical cyclone, tropical storm Beryl was a tropical storm, had about 35 knots. We always use knots in our business. I know that drives some people crazy if they're in the metric system. But in any event, it was about 35 knots, and the official forecast was for it to become a moderate category 2 storm within about 3 days. Okay, so the forecast and the observations were okay. I'm showing you some examples. I'm not showing them to criticize in any way, shape, or form forecasters. They have a big job. It's just to show that nature sometimes has a solution that's different than the forecasters think. And nature, basically, in this case, this was just from last night. I just put this slide together last night. Mark Booth and I did this, and it was 130 knots, and it's about 150 miles per hour. So it's a very strong category 4, just on the edge of category 5. Okay. So the models have challenges with these systems. That's the point. Right? The models have challenges. We still have a ways to go with all the models. Okay? We can make the models better. You might say, well, maybe the models don't have enough resolution. Maybe the models don't have the proper initial condition in terms of wind, in terms of pressure, in terms of moisture. That's probably all true. It's probably all true. Some of the models, this one in particular, the H-WRF model, that's the hurricane version of the WRF model, weather research forecasting model that we use in the United States. It's actually used globally in certain forecast agencies. This model is being run currently, I believe, with a horizontal grid spacing in the fine mesh. I believe it's either 3 or 2 kilometers. That's not bad. It's not bad. It's not an LES model by any shape or form, but it's not bad. I mean, the ECMWF in comparison, the European model is, what is that? I don't know. I can't remember what they're down to now, but I think it's maybe 12 kilometers, 16 kilometers. So you get down to that tens of kilometers, single tens of kilometers, you have this problem between whether you're trying to resolve the convection that represent these up-down motions in the clouds, or you're trying to parameterize the up-down motion statistically. You get into kind of this no man's zone, so that's kind of an issue. But in any event, the models still have a ways to go. But I do think that the resolution, the initial conditions are an issue. Even with reconnaissance aircraft, we've been flying reconnaissance aircraft through this system the past several days from the Air Force hurricane hunters. And the forecasters, basically, this is data based on the forecasters at the National Hurricane Center. So they've taken the data and they've decided what they think the intensity is from the dropsondes and the aircraft reconnaissance. Okay, now I want to just convey to you what it looks like when a storm forms. Some of you already know, but some of you may not. So I wanted to show an example. I'm going to go back to a different storm. I'm kind of showing a lot of storms here. It's okay. We still got a little time. So this is Hurricane Sandy. I'm just going to show this loop quickly. It's an infrared loop. And it shows the infrared looking at the infrared, you're looking at the infrared temperature emitted from clouds, okay, in the tropics. And it's color enhanced. And the red regions are cold, like minus 70 centigrade. So it's like 200 Kelvin. And there's lots of convection taking place. This is prior to Hurricane Sandy, 2012. And what we know is that a very weak easterly wave came in, and it basically provided enough of a protective region that allowed convection to kind of operate and be somewhat protected from the environment. And then you see the relatively rapid spin up of this system within this region, which I won't go into, but it became a category 3 when it crossed Cuba. And then it basically moved up the Atlantic coast. Forecasters thought it was all done. The ECMWF model predicted it would do this, and the United States model predicted it would do that. Guess which one happened? The ECMWF model, I think, got it right, and the model went into New Jersey. The storm went into New Jersey, and it caused catastrophic flooding, so it was like $70 billion of damage. But of course, it formed down here in the Caribbean in this time of October. October is always an exciting time in the Caribbean. That's when things really start to spin up. Okay, so what are we studying? Why do we need this new paradigm, rotating convection? Well, I think I'm going to try to answer that in the next few slides. To forecast or determine possible changes in climatology as a result of global warming, and to better forecast these systems, we do need a conceptual model of how tropical cyclones work. A basic question, for example, is, a very pertinent question, is how do they form, how do they intensify, and how do they decay? Okay, seems very basic. A subsidiary question is, why do they sometimes intensify rapidly? I've illustrated that with a couple of examples. Sometimes unprecedentedly rapidly. In the case of Beryl, it's, I think, almost, it's one of these upper echelon storms that forms very early in the season, whether it's the first to do this, but it's in a rarefied point in the statistics, but they often intensify rapidly. We need to understand why that is. And what conceptual models are available to address these questions? We have several conceptual models in the literature. If you open up Jim Holton's book, you learn about the wishing model. You have some other models that go back much longer in time, what we call the classical model. We also have CISC. CISC is basically dead, so we'll put it off the table. You have the wishing model, you have the classical model of spin-up from Biko-Oyama, for example. But those models are axisymmetric. I've just shown you an example of genesis of Hurricane Sandy. It's by no means axisymmetric. It doesn't occur in rings of convection, like bicycle tires. You don't see rings of convection organizing. Convection is very sloppy. For those of you that have dogs, Chien, when you serve them dinner, do they care if the dinner's put in an orderly fashion in rings? No, they care about the food you put in the plate. So it's more like a dog's dinner, like Chien's dinner, than it is an axisymmetric rings. So we need a model that's basically three-dimensional. And we need a model that's based on physical principles, like conservation of absolute angular momentum, or a model that the analog of that in 3 dimensions is the change in the circulation around some material or some fixed circuit around the atmosphere. Okay, we need a model that's generalized, and it's not just axisymmetric. Okay, so basic ingredients. Here's just a couple simple laboratory experiments that we believe are very useful. The one is the deep convective forcing experiment due to Turner and Lilly back in the 60s. They were using this for tornadoes, but we believe we can use this for hurricanes. What they basically have is air bubbles. They have a little tube, and they basically force air through this tube in a rotating tank, and the air basically comes out of this tube in bubbles. The bubbles rise in the fluid. As the bubbles rise, they drag the fluid with them. Okay, so they essentially exerted a force on the fluid by drag, and the fluid that's being dragged upward has to basically draw the air draw fluid in from the side. That motion, that inward motion, of course, has to come about through a radial pressure gradient force, 1 over rho d PdR. And as you draw the fluid in towards the center, because of the bubbles, the rate at which you're releasing the bubbles, there are two forces that are acting to oppose that, of course. One is the centrifugal force, V squared over R, and the other is the Coriolis force. The centrifugal force, centrifugal is a French word, centrifuge, and Coriolis. Both of these forces, I guess, have French origin. That's pretty important. So both of these forces act outward. They're trying to oppose the drawing in of the fluid. And the pressure gradient force is, of course, trying to draw the air in towards the center, because that's what's basically required as a result of the bubbles rising in the fluid. Now, in the tropical cyclone, it's not as simple as just an imbalance of these forces. Because in the tropical cyclone, the radial pressure gradient essentially is in balance with the centrifugal with the Coriolis force. Okay? And of course, the Coriolis force is due to the relative motion of the fluid relative to the tank. And you're essentially in a state of what we call cyclogeostrophic balance. We call in the United States gradient wind. Actually, I like cyclogeostrophic. That's the French term I picked up at Nice at EGS about 20 years ago. So it's a little bit more subtle because you have a balance of these forces, but that's okay. We can replace this forcing with the diabatic heating rate. We can replace it with the entropy, change in the entropy of the air. Okay, and then we can basically use the same idea. Now over here on the right is what we call the boundary layer friction experiment. We got got fluid in this teacup, and it's spinning. You impart spinning motion with a spoon. And what you see is the tea leaves, as they fall from the free surface down to the bottom, they tend to congregate in the center. We all know why that is, because there's an imbalance between this pressure gradient and the Coriolis and centrifugal. In this case, we don't have a Coriolis in this case, because we don't have the teacup's not spinning. But there's an imbalance of these two forces because there's a boundary layer here. And the boundary layer tends to impede the motion in the azimuthal direction. And that imbalance of forces, basically the radial pressure gradient that's established in the rotating, in the spinning fluid, is basically transmitted through the boundary layer by the boundary layer approximation, Prandtl's boundary layer. But the tangential wind, tangential velocity is slowed down by friction. So this force, basically, it may be in balance with the pressure gradient in the bulk, but in the boundary layer, it's not in balance, and the imbalance drives that flow towards the center. But the flow towards the center has a result that the flow basically is mechanically lifted out of the center, and it's forcing air to move away from the axis of rotation above the boundary layer. So friction always causes outflow above the boundary layer. If you remember an ice skater, as she's spinning quickly, she moves her arms out, she slows down. So friction is always acting to spin down the fluid, and the bubbles, or the convection that we're talking about, we just saw examples of, are trying to draw the air in and spin up the fluid. So there's of course, a competition between these two processes. Basic physics, that's all it is. It's very basic physics, okay? Of course, the basic principle that we're going to use to understand this is the principle in which if you assume that there's no friction acting above the boundary layer, and you assume that the flow is axisymmetric, which is not in general, so we'll have to talk about the azimuthally average flow. But for simplicity, just for a moment, we can talk about strictly axisymmetric flows under the assumption that there's no torque acting on the azimuthal direction like a pressure gradient force, and there's no friction, then the angular momentum given by this quantity m is materially conserved. So m is the sum of the relative and the planetary angular momentum. The relative angular momentum is the product of the radius from the axis of rotation times the tangential velocity, and the planetary angular momentum is 1/2 f times r squared, f being the so-called Coriolis parameter, which is 2 times the Earth's rotation rate of the Earth times the sine of the latitude. We're in the tropics, so the sine of the latitude is small, but it's not zero because we're not talking about spinning up a hurricane on the equator. That's another topic. It's kind of a special topic. For people in the business. We don't get hurricanes forming at the equator, though in principle we could if we had some initial circulation that just happened to get advected down near the equator. Everything we've discussed will still take place, and we've actually shown it does, but near the equator. But so if you conserve angular momentum materially, if this particle moves in, then you decrease the radius. If m is conserved, well, you can solve this complicated equation for v. That's a joke. You get basically m over r minus 1/2 f times r. If m is conserved as you move with the parcel, if you're above the friction layer, then as you decrease r, you amplify v because m over r increases, and you also amplify v because you're subtracting less from the m over r. So both those terms are contributing to an amplification of v, and so if r decreases, v increases. Similarly, if r increases, v decreases. But to spin up a vortex, you need to have m surfaces moving inward. And you can generalize that in 3 dimensions to talk about a flux of vorticity across a fixed loop. And you basically change the circulation by drawing vorticity across that loop. Okay, that's the simple generalization. In the friction layer, we know the friction in a fluid, the fluid velocity is brought to rest, okay, at a solid surface because there's no slip. But in a real hurricane or tropical cyclone, any vortex boundary layer, when there's tornadoes, hurricanes, it's a little bit more complicated because why? Because there's a secondary circulation that's superimposed on the primary circulation. We already discussed it a minute ago, but I'm going to illustrate it here. If I can play this movie. So it's a simple movie. You put tea leaves on top of the teacup, and you impart angular momentum to the teacup with a spoon. And the tea leaves, of course, are circulating around the teacup, but they're also a little bit heavier than the fluid. So they sink, so they slowly settle down to the bottom. But of course, the secondary circulation that's acting on top of this primary circulation, this overturning circulation, as we discussed, the imbalance of forces in the boundary layer drawing the tea leaves to the center. But as the fluid is rising out of the boundary layer, it's basically forced to diverge, and so the fluid slows down very quickly. It's slowing down by the secondary circulation, by the fact that you have outflow above the boundary layer. And it's causing the arms of the ice skater to move out. It's slowing it down much faster than you would have if you just were to diffuse the angular momentum of the fluid into the lower boundary. That would take a lot longer, as we all know. Okay, that was all kind of an introduction, but let me just get to now. So I'm going to skip that. I'm going to skip this. These are the equations of motion. We have this cyclogeostrophic balance in a tropical cyclone. Primarily, these terms are balanced above the boundary layer. And in a tropical cyclone, we have primarily a hydrostatic balance, and we essentially have an elastic balance. But it's the deviations from that balance that cause the spin up or the spin down. Okay? And we have to add the moisture equations into the problem. So here's a simple thought experiment to understand how a vortex spins up and maybe later spins down. We have initial vortex. It's in a numerical model. We have a tangential wind that's only 5 meters per second. It's initially cloud-free. It's over relatively warm water. It's in a tropical environment. And you basically examine the evolution of the atmospheric variables in this simple environment. And what you see is, of course, you would expect the vortex would spin up. So you might say, well, we're not learning anything, Professor. We already know the vortex would spin up in a favorable environment. That may be true. But why is it spinning up? And how is it spinning up? Okay. So the vortex undergoes an intensification. Maximum winds intensify. The size of the vortex given by, say, the maximum wind that decreases rapidly down to a very small scale, like 10 kilometers. The size of the vortex as defined by the radius of gales, the French Navy are concerned about this. You don't want to sail inside the gale region because they're very strong breaking waves, very high waves. It can be very dangerous for ships. So the breadth of the system is basically increasing, as well as the size of the system is decreasing, as defined by the radius of maximum wind, but the breadth is increasing. Okay? And this is the strength of the updrafts as easily averaged. But if you look at the fields carefully, and I'll get to this, I only have a few minutes. If you look at the fields, this is the tangential wind time series for reference. This is the vorticity. Okay, the vorticity, for those of you that everybody knows the vorticity, is the spin. The spin of particles. Okay, it's a physicist's dream. Vorticity everywhere, right? In this case, the spin, this is in red. You have cyclonic spin, that's spinning in the same sense as the Earth. And the blue is the anticyclonic spin, that's spinning in the direction opposite to the Earth. To form a hurricane, you want to have a lot of red spin come together. And right now, there's lots of isolated regions of spinning fluid, and then there's updrafts, which you see here by the aqua and the yellow. Yellow is at 6 kilometers, and the blue is at 2. It's just a 1 meter per second vertical velocity contour. This just gives you an indication of whether the updrafts are kind of vertical or whether they're not coupled in the vertical. So they tend to be more or less vertically oriented during this process. So I'm not saying they're barotropic, I'm just saying they tend to be somewhat coherent updrafts. And if you look carefully at this time when the vortex starts to intensify, a dramatic change in the vorticity has occurred in association with this slow inward moving air above the boundary layer that's helping organize or bring the vorticity together. And then the vorticity starts to merge in that sense. But the secondary circulation is a very important part of that collection process. It's an aggregation process, okay? At later times, the winds spin up, and the vorticity is clearly suggesting that it's organizing. The convection is starting to consolidate around the center. You're starting to get contiguous regions of updraft. And in the outer region, the winds are spinning up so strong that the convection that forms out there tends to be sheared. So you get into a regime outside of the core, what the astrophysicists call spaghettification. That's what happens outside of the event horizon in a black hole. Okay, you get this debris field outside of a black hole. You get strong shearing motion in a rotating black hole. Okay, so you can get the same sort of thing in a tropical cyclone. You get what we call axisymmetrization, spaghettification. All right, so we can take an azimuthal average. We can look at the azimuthal average picture of the development by taking an average around a ring. And this is what the azimuthal average picture. So you can look at the microscopic view, or you can look at the macroscopic view. You can do both. And in this case, I'm going to animate this. Can I do it? Just have a few slides left. So I animate this. What I'm showing here is this radius and height. I'm looking at a cross section through that whole domain. It's a very big numerical simulation, but we're just looking at the inner region. The yellow contours are the M surfaces, or the circulation surfaces. M is increasing outward. Okay, at this time you see a little bit of inflow. The blue is inflow, radial velocity. The red is outflow. So blue is coming in, red is going out. Yellow are the M contours. You watch the M contours being drawn in the lower troposphere, low to mid troposphere. They're being drawn in as you would expect, as the ice skater is intensifying his or her rotation. These black contours are just isotachs of tangential wind. But basically, you see this when the convection starts erupting. It's almost a bit of an abrupt transition. But on a broad scale, what you're doing is you're obviously collecting. You're drawing in the angular momentum. Now, the angular momentum is not conserved in the friction layer because it's transferred to the ocean. But above the boundary layer, you're tending to draw the end surfaces in. Above the boundary layer, where there's inflow above the boundary layer, that's acting to counteract a frictional effect, which is tending to produce outflow above the boundary layer. So the inflow is on a broad scale is doing that. Okay, now, so this is the rotating convection paradigm in general, and it's a generalization of the angular momentum equation. And it basically recognizes the flux form of the vorticity where the vorticity has these two components, the vective and non-advective components. For now, we can just think if you draw a vorticity in across the circuit, you're going to increase the circulation. That's just think of it like Stokes theorem. Everybody knows Stokes. Okay, so if you draw a vorticity in inside of a fixed circuit, you're going to increase the circulation, the average tangential velocity around the circuit. So the convection is doing that. It's drawing in, it's acting like, I'm not going to use the word vacuum cleaner, but I'm going to say it's a natural version of a kind of a collection process, which is entraining the air on the side of the convection to draw the air in above the boundary layer and help basically increase the circulation. But the convection itself is spinning. It's rotating, okay? So they are rotating convective elements there. Okay? But of course, as you spin the vortex, as you intensify the vorticity by stretching, you also decrease the cross-sectional area by conservation of Kelvin circulation. If you follow that circuit, Kelvin circulation, and decrease the cross-sectional area, the vorticity goes up, but you're not changing the net circulation around the convective region. So you need to bring in vorticity across that circuit to increase the circulation. So you need that inflow above the boundary layer to increase the circulation. Okay, I'll just say that in three-dimensional models, did some work with Jim McWilliams and my colleague John Persing. We showed basically that the eddies, or the non-axisymmetric processes, can act in counter-gradient ways compared to what you would predict with just diffusive reasoning, just diffusion. Okay? They act in a very different way to help concentrate momentum horizontally and vertically. Okay, so three-dimensional aspects of the convection is important. So here's just a summary of the model. Basically, we spin up the vortex in a broad sense by drawing in air above the boundary layer. And in conjunction with the angular momentum conservation principle, we amplify the tangential wind by increasing this term, the m over r term, as m is conserved, and r is decreasing. And we also increase v because we're subtracting less 1/2 f times r. Now, in the boundary layer, there's transfer of m to the ocean. But we also have transfer of energy from the ocean to the atmosphere. So we're evaporating water. The water is then being collected towards the center to feed the clouds. The water is necessary, of course, to feed the clouds to continue the latent heat release process. So the secondary circulation in the classical model, the boundary layer is a sink of angular momentum, as you would expect it to be, but a source of energy in the form of latent fluxes that are basically enriching the boundary layer with moisture. Of course, you also have downdrafts that are in the shallower convection I showed earlier that are tending to dry the boundary layer, trying to warm and dry the boundary layer, but the moisture is tending to offset that. And in this inner region, the increase of the winds is basically helping moisten the boundary layer significantly to feed the clouds that are needed to continue to maintain the convection. Now, that explains how the broad scale circulation spins up. Okay? But how about the eye wall? And where's the maximum wind? Well, the maximum wind, actually, I didn't go into detail. That occurs inside the boundary layer, kind of in here, at about 600 meters, 700 meters right off the ocean. Boundary layer might be more like a kilometer, 800 meters. The maximum winds is like 500, 600, 700 meters. That's well within the boundary layer, well within the friction layer. You might ask, well, that can't be right. Friction tends to slow things down. Locally, friction tends to slow things down. But locally, you can actually enhance tangential wind and increase the wind beyond the wind above the boundary layer because you have strong convergence. And if you have strong enough convergence, you have strong enough inflow in the boundary layer, then if you basically can bring parcels in to the center quick enough, then if you lose angular momentum, if you don't lose it very rapidly, then you can take advantage of the fact that you're bringing parcels in and you're losing angular momentum at a lower rate than you're bringing them in. So you can actually get into a regime where you increase V even in the boundary layer. Okay. Now that high wind is then lofted into the eye wall, and it's spinning up the eyewall cloud in the form of eddies and also in the form of mean transport. So there's really no difference between the formation and the intensification process in terms of basic physics. Basic physics doesn't care. We would argue there's no real difference. People have discussed how genesis is very different from intensification. We don't think it is. We think it's basically the same processes that are at work. Our numerical simulations are supportive of that. Our observations are supporting that. Now, I will point out one thing. I'm going to talk about this tomorrow at Midi-Pyrénées. There's a subtle thing that happens when the storm gets strong. Storms don't last forever. And you might say, well, that's obvious because they move into high latitudes. That's true. Higher latitudes, colder water, stronger shear, mid-latitude westerlies, colder air. Of course, storms don't last forever, but even in an idealized configuration, kind of like an idealized planet formation, storms don't last forever. And part of the reason for that is you have to supply the storms with angular momentum. You're losing angular momentum at the ocean all the time. And that angular momentum then is basically about the angular momentum of the parcels that are rising here is less than it is when it started. So that angular momentum in the upper troposphere, if you're going to imagine like a Carnot machine, Gary Manuel's very nice articulation of this about 30 some odd years ago, still provides a useful zero order kind of description of the mature hurricane, but it has limitations. But in order to get that low angular momentum replenished, you have to supply a torque on that fluid in order so the parcels, when they come down and start over again, they have the same value of M when it starts. So that's one reason why they don't last forever, because you don't typically have an artificial source of angular momentum in the upper troposphere. The second reason why they don't last forever is something very interesting can happen in the interior region, and that is the boundary layer, the frictional boundary layer, is basically driving flow in towards the center. And it basically doesn't care about all these details of the tangential wind field, because it's the radial pressure gradient that's driving the air towards the center. If the convection is not able to keep up with the air that's basically being supplied to it, it doesn't have enough buoyancy in the eyewall, the convection is going to sputter. It's going to sputter. So that air, instead of it being lofted to the upper troposphere, is going to flow outward. When that happens, the convection is not able to ventilate the air the boundary layer is delivering to it, and the vortex can spin down. And what we've discovered is this can happen at a later stage of the vortex evolution. And you get to a point where, the upper troposphere is warming because the winds are intensifying, and by thermal wind balance, you have a warm core there, and it's getting warmer. But the boundary layer is also humidifying because there's constantly evaporation that's taking place. And the boundary layer is getting more moist. These two things together are kind of setting up a situation where the convection is basically not as unstable as it needs to be in order to loft the air to the upper troposphere. And the boundary layer dynamics basically force the air up, and then they have a higher tangential wind here, so they're centrifuged out. So the centrifugal effect is very pertinent in this problem. And the flow is not in gradient imbalance here. And so the vortex spins down rapidly. So it can undergo a very rapid decay, even in the presence of an infinite amount of energy, essentially. So it's like the death of a star. In this case, the star's not killing itself because it's running out of nuclear fuel. It's killing itself because the convection is not able to keep up with what the boundary layer is delivering. The boundary layer is delivering a very large amount of mass flux. And the larger the vortex gets, the stronger the boundary layer inflow, because the stronger the radial pressure gradient. So it becomes a losing game. As the system gets mature, it's very difficult for it to continue to intensify. It won't. If the conditions are right, it'll spin down rapidly. Now, many people think storms undergo these fluctuations in intensity because vertical shear is acting. That may be the case, but what may happen in practice is that the vertical shear may be modulating the air that's getting into the system, and it may be basically exciting this unventilated air in the inner core and causing these fluctuations. So there's some very interesting things that we need to explore as a result of this, and we've discussed some of these things in our book. I'm not trying to make money off this book. We only get $2 per book, so please don't be offended. But we've put about 17 years of our time into this book because we had to try to figure out some of the mysteries about the Wishy model and some other things. So it took us quite some time to figure out what was going on. We're writing about that now. Most of it's discussed in this book, but we've made a few discoveries in the past couple months when we had a dinner with Kerry Emanuel in Long Beach, and we discovered, he confirmed our suspicion that the Wishy theory does not conserve angular momentum. So his theory for spin-up, his analytical theories for spin-up, do not conserve absolute angular momentum above the boundary layer. So if you don't conserve angular momentum, now you have a source of angular momentum. So a lot of things can happen when you have an unspecified source. So you're getting into dangerous waters if you start throwing out equations. And this is a discovery we've just made, and it's actually quite interesting. Kerry admitted this to us, so he doesn't disagree with us. He might say the source isn't large, but we have a formula for the source, and I don't think it's that small. So in any event, this is basic principles. There's no tricks, as my Russian colleagues tell me. So there's no mystery, no magic tricks in this book. So anyway, thank you for listening, and thank you very much for having me.
Thank you, Mike. Question, s'il y en a en anglais, possible.
Thank you for this very interesting talk. I was wondering about the angular momentum loss of the air into the ocean, and wondering about how this angular momentum absorption by the ocean could change the currents in the ocean. Does this have an impact on the circulation, or let's say medium scale currents?
That's a very good question. Actually, it does have an impact locally, because the winds of the tropical cyclone impart a very strong stress, 10 times greater than the average stress. The average stress might be, the atmosphere is like 0.1 newtons per square meter. So the typical stress in a hurricane might be 1 to 2 newtons per square meter. So at least an order of magnitude stronger, and it produces this inertial type oscillation in the ocean, kind of to the right and in the rear of the system. And that inertial oscillation produces strong currents in the upper part of the mixed layer. And those strong currents are then gravitational shear instability. So that produces a lot of mixing underneath the ocean. And that basically contributes to a strong upwelling of cold liquid underneath. So it tends to cool the ocean behind it. So these systems tend to leave a fairly prominent temperature wake behind them. Not so much of a strong current, though. It's persistent. This strong wake behind these tropical cyclones. Some have suggested, Kerry Emanuel is an example, he suggested, I think 20 years ago, that the wakes behind these tropical cyclones, in an aggregate sense around the globe, could in fact account for, at that time, kind of this missing petawatt of energy that the oceans were believed to be transporting to the pole. Because there's this cold wake, and that kind of requires a response to ameliorate that wake. And then some work has been done, and that petawatt's been kind of knocked down to like 1/10 of a petawatt or less. But it's an interesting idea, okay? But it's not a persistent imprint on the Gulf Stream, or is it a persistent imprint on the overturning circulation other than through this cold wake? But that may be tenths of a petawatt in an aggregate sense. But that's a question that's being considered, because there's a big, many people in the room know this, large community of people trying to understand the meridional overturn circulation of the ocean. What's driving it? And there's kind of several proposals on what's driving it, whether it's the tides, tidal motions dissipating, and then, or whether it's the fishes inside the ocean, or whether it's, salinity, obviously, the thermohaline circulation. But Carrie was suggesting that maybe it's a result of this mixing in hurricanes that might be contributing to that. So, the question's not, it's not out of the ballpark. It's interesting. But it's, as far as wind, as far as currents, it's kind of a local effect. But I should say that behind a hurricane, that's where the cold temperatures are. So as the storm moves, if it doesn't move, of course, it's just going to upwell that cold water right underneath it. So it's going to tend to kill itself. So as the hurricane moves, fortunately for the hurricane, as it moves, the upwelling that's taking place is behind the system. So a lot of the work we did in this first book is not considering the air-sea interaction process. But in the second book that we're planning, we want to consider the air-sea interaction, the modification of the ocean, and the coupling of the ocean circulation with the atmosphere. We had to understand this atmospheric problem first. It was just too perplexing for us. It took us 3 days to realize in 2006 when we met in Germany that we didn't understand anything. Okay, yeah.
So just when you start your talk, you give us some examples like this one of how numerical models fail. And then a lot of your talk was pitching the axisymmetric model against the non-axisymmetric model, which you're saying that these rotating convection is very important, and of course you can't have that in an axisymmetric model.
No.
But the numerical models, I mean, assuming they get the convection right, you'd expect them, they're not axisymmetric, you'd expect
Correct.
to get the vorticity dynamics right.
That's correct.
So
Yeah.
from this opposition of axisymmetric versus non-axisymmetric, is there a way you can put your finger on what's gone wrong with the numerical models?
Not yet. Maybe someone else smarter, much smarter than I am. Maybe we can work together on it. But I mean, as I said, it could be resolution, it could be initial conditions, it could be the convection still may not be well represented even at 3 kilometers. May not be representative of real convection in the atmosphere. But some of these other models are not at 3 kilometers. Some of these are at, they have larger grid spacing. So could be a number of these factors. I haven't put my finger precisely on it, but we need to look at the model simulations with some of these new ideas in mind. Help try to understand what are the models doing. Okay. Our point is that if you use the wishing model, at least for us, we've been very confused with many questions about what's going on. Harry's not confused, but that's okay. I mean, I've told him I think it's not useful. He didn't like that. Okay, we're friends. He was on my committee. So what? You can have a good disagreement. Because it's not consistent with observations. If you have a theory that's not consistent with observations, no matter how beautiful it is, we question it. Okay. Actually, Richard Feynman has something to say about that, but I won't go into details. Those of you who know Richard Feynman, then you probably know the famous quote that I'm talking about. Yes.
Thank you for this very nice talk, Sibyl. I wanted to go back to the question of ocean-atmosphere interaction.
Yes.
The context is 20 years ago with Swen behind me. We did a couple of simulations showing that the feedback effect of the ocean to the cyclones are much less in a full 3D model than in theory by Thierry Emmanuel because of the radial advection of humidity. So I wanted you to know if you could comment on that.
Well, my simple answer is, that's very interesting. I want to learn more about it. And my simple answer is, if you have a model, and you built a model, doesn't conserve angular momentum above the boundary layer. There's a lot of reasons why things are not going to work. I know that.
In this case, it's the advection of humidity that it doesn't have at all.
Oh, I can't. I mean, I'm sure he has that, but how that interacts with the convection, and then the source of angular momentum is not clear. And see, the problem is if you have a source of angular momentum, you have a hidden variable, you don't know what's going on. Okay, it's taken us 20 years to figure this out. Okay, and it's not something that a lot of people that study wishy even know about. You're not even aware of this. And it's actually something we've, we've assumed. We've always assumed it's been conserved. And we've discovered it's not. That's a problem. Now, I'm not saying that obviously it's not conserved in the boundary layer. That's not what I'm talking about. I'm talking about above the boundary layer. I mean, the point is, this result that you mentioned is very interesting, and I have no reason to doubt it. I think it's probably something I need to learn a lot more about because.
I can send you a paper.
Oh, please. Well, you can give it to me while I'm here. You can put it on thumb drive. But the only way to spin this vortex up, the convection basically has to draw the air in above the boundary layer. It has to do it. You can't spin the vortex up by just drawing air in the boundary layer because you're diffusing angular momentum to the ocean. You can't spin up the vortex by just the boundary layer inflow alone. You have to have inflow above the boundary layer and at the top of the boundary layer where friction is zero. You have to do it. And it's just been puzzling to us because all of his main cartoon that we discovered in 2000 has the air basically flowing outward, always flowing outward. It's always outward above the boundary layer. We're always puzzled, how do you spin the vortex up? So it all boiled down to, I'm getting into technical things, so it's inside baseball stuff, okay, or inside soccer stuff, okay. It all boils down to what's going on right at the top of the boundary layer. So you get into this whole question whether it's a singular delta function there, a direct delta function, and all this. But then once we discovered you have a source of angular momentum, it's not that at all. It could be completely different. So you can do anything you want. Anyway, yes. So if you want to try to put your finger on what the models are doing wrong, what we're suggesting is let's use the rotating convection paradigm framework to try to get at this question. Okay? Don't use wishing. Okay? That's what I'm saying. Yes.
I have a curiosity question about the reconnaissance flight across at the beginning you mentioned.
Yes.
What does it target? What kind of feature does it target when they observe the cyclone before it lands?
Well, the National Hurricane Center forecasters, what they need, they do updates every 2 or 3 hours, and what they need is real observations. So they send the airplanes in to the center, and they have the airplanes, at least the C-130s, the aircraft, the Air Force hurricane hunters. They have the hurricane hunters cross through the storm, go around, and come across again. And they do that, I don't know how many times. They do it as many times as possible before they run out of gas and they have to come home. Now, when they do this, they're able to infer the surface pressure. They're able to calculate the winds from GPS and they also are dropping dropsondes, and they're taking, they're recording flight level data on board the aircraft because the aircraft is moving, and so the GPS keeps track of the aircraft's motion. You can infer the wind speed, the relative wind speed around the aircraft by doing this along the flight legs, okay? But they're also collecting Doppler radar. And so you have a radar instrument on the P3. It's not the C-130, I don't believe they're flying with Doppler radar yet, but anyway, that's another, they have radar, of course, as the pilots flying in. I'm sure there's some pilots in the room here. So they have severe weather avoidance radar in the cockpit, but they don't have a Doppler radar scanning the atmosphere. The NOAA P3 aircraft have the Doppler radar. But the hurricane hunters tell them to fly in and around the center. And the center is, at this point, once it becomes mature, it's you know where the center is. So you can deploy the aircraft to that center. But at the very early stages of a storm, to say, you don't know where the center is. Okay? And so if you're going to design an experiment to study the genesis process, this is Raphael that goes off. It's off in the Atlantic. It doesn't affect anyone except for boats, okay? But this system, Sandy, you know, they were looking at this, nothing's going on. This is just the tropics in October, lots of convection, boom, 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 no big deal, you know, it's like convection in the sun, you know, boom, 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 boom. Okay, but now, woof, there's a little rotation there. Whoa, what happened? Where should I fly the airplane? Where should I fly the airplane? Should I fly it there? Or should I fly it there? Oh, hang on. Oh my gosh, it's spinning. Oh my gosh, it's too late. The problem with Genesis is to deploy the aircraft, you have to have enough time to get all the pilots together and put them on the airplane and fly them down. So when we did the Genesis experiments, we were sitting out of St. Croix here for 7 weeks. We were studying storms forming days before the forecasters even cared. And it's very difficult to get the agencies to commit aircraft time to go out and fly nothing. So we use this marsupial paradigm, which everybody knows what marsupials are. Kangaroos, wallabies, the idea that, you know, the mother rears her children in little pouches. And when the babies in the pouches are grown up, they jump out. But in the pouch is a very nurturing area, okay, for growing the babies. So I know you think this professor from America is kind of crazy. However, it's a very, very interesting and practically shown it to be correct. That within the easterly waves themselves, Nick Hall's worked on easterly waves, some very good work. There's a region inside an easterly wave called a nonlinear critical layer, where the wave speed is coincident with the mean flow speed, and you get what we call a nonlinear critical layer. And you get a little region in there which is protected. And so the storm forms there. So the answer to where you want to fly is you fly to the center of that pouch. And you may have convection forming in different places. Keep flying the center of the pouch. The point is, keep flying that. And if the environment remains favorable, the convection will eventually emerge there. And that's what we showed and predicted. We verified that theoretical prediction. So it was marvelous. We predicted that the attractor of the convection in the atmosphere was where the trough axis and the critical line intersected. So that was the strange attractor, if you will, of the tropical cyclone. It was kind of at that point. And that's where, so basically we've done work on this easterly wave, which harbors the initiation and the accretion of vorticity in this region for Sandy. And it's basically near this sweet spot where the thing forms. And so at early stages, my only point is it's hard to determine where to fly. Our theoretical work has given the answers to where to fly. Now we just need to get the agencies to say, okay, I'm going to spend another $100,000 or maybe $1 million, $2 million, and I'm going to fly systems 2 or 3 days before forecasters even care. And so you're not typically going to get any buy-in from any agencies to do that. NASA won't do it. NOAA won't do it. Air Force won't do it. Not until the hurricane forecasters tell them to go. And then they have a mandate to go. So politically, everything's good once the forecasters say go there. But in the scientific experiment we did with the National Science Foundation, we were able to go several days, 3 or 4 days in advance. Then you learn something about the early formation. Okay. All right. I think I answered your question. I probably answered a lot more, but I probably gave you a lot more information you even wanted to know about.
I understood that to maintain the hurricane, it has to displace because if it's to maintain the energy flux and convection.
Yes.
And so do we know, do we have a clear idea of the mechanisms that are involved in the displacement of the hurricanes? Because sometimes it's moving very fast.
Yeah,
And
it's true. That's true, actually. This case of Beryl, I don't want to interrupt you, but this Beryl was moving at about almost 20 knots, maybe not 20 knots, maybe 16, 17 knots, which is almost 10 meters per second, maybe 9. Moving pretty quickly. But nevertheless, it underwent this rapid intensification. Now, typically, these storms form, and they form in the tropics, and they form in the easterlies. So the trades, basically, except when you're in the Western Pacific, where you have the monsoon, when you get into that. But in the City Atlantic, the winds are basically carrying the disturbance with it. So the storms are moving because they're embedded in the trading lines. And that's essentially the first order, the deep layer mean.
It seems that when
The deep layer mean is what determines the motion. There's a beta effect, which is that tends to steer the storms forward, away from the equator, with the beta gyres, which I can get into. That's an asymmetric vorticity effect.
Yeah, but it's quite, usually it's the beta gyre, the motion is
Weak.
not that fast. Yeah.
That's correct.
Yeah.
Yeah, the beta gyres may be a couple meters a second.
Mm.
You know,
And it seems that when they form, they are quite stationary, and then once they are formed, they move northward quite rapidly, at least in your observations.
Yes. I wouldn't necessarily say they're stationary, but they're moving. The storms that form off of Africa, for example, easterly waves come off Africa. The easterly waves are moving at about roughly 6 degrees longitude per day, which is roughly 6 meters a second, let's say. So they're moving at about, roughly 6 meters per second, which is 12 knots. So, and when we see these systems forming, they're typically moving in that wind. I wouldn't say they're stationary. Not exactly.
Yeah.
Okay.
Another question I had is associated with subsidence, because you said it was part of the system but I don't understand why. What's the role of subsidence in this maintenance of convection or whatever for the life of the vortex?
I see. One second. Un moment, s'il vous plaît. I think you're referring to this comment I made here. Yeah. I've only depicted in the schematic the deep clouds in the eye wall region, but there are also rain bands and other clouds in the outer region. And the air that's sinking outside of those clouds, some of that air, and these clouds are also raining, so they're producing downdrafts that are advecting lower energy air into the boundary layer. And my point was that subsidence, or that downdraft driven air, is delivering lower entropy values to the boundary layer. And so the moisture evaporation that's taking place in the boundary layer is tending to offset that negative input coming from the downdrafts of these clouds.
But I mentioned the subsidence in the eye.
Okay. So this comes about through a very small imbalance of forces, has to always, right? Between the pressure gradient force in the vertical and the gravitational force in the vertical that's downwards. And so you basically get a very small imbalance, and that's essentially caused by the compensating subsidence from the upward motion in the eye wall. There's compensating subsidence on both sides. And so you get basically weak but persistent. Like the difference between when you turn on your faucet, you turn it on really rapidly, or you just turn it on, there's a little bit of a drop, mainly like that. It's kind of relatively weak subsidence, but it's persistent and occurs over days. So the air kind of slowly subsides in the eye. And it gets very dry up here. But there's typically a region here around about 10,000 feet. You may get some stratocumulus in the eye. You get what we call a hub cloud in there. You get a little more convective convergence in there, but there's an inversion there. And the air basically is very stable, very warm. So the lapse rate basically is you get a very stable layer here. And so this air is relatively dry, and this air down here is very moist. Almost 100% relative humidity, almost. Very moist, very high theta E's, very low pressure. But this subsidence is coming about in this small imbalance between the pressure gradient force and the gravitational force. The air that's coming in here and the outside is coming through primarily through, it's coming through a combination of frictional induced subsidence from the boundary layer because the air is accelerating down the pressure gradient. The air is basically, it's accelerating, so it causes basically a divergence here. And it's also coming from downdraft air. So that's air that's being driven by precipitation downdraft. Obviously, there's a lot going on in these systems, but this cartoon is simplifying, kind of focusing on this region here. How do you spin up the max? Okay. How do you spin up the eye wall, per se? Okay.
On va prendre la dernière question.
Thank you very much for this very interesting presentation. I would like to know if you have already observed or if you are forecasting some change in the behavior because of the global warming, and in particular the warming of the Atlantic Ocean.
I'm not doing any forecasts of that per se. I've got my hands full with just trying to understand how the system works in the light of hidden variables that we've discovered, or hidden sources. But there are people that, of course, are thinking about this problem seriously. And so there's been a number of modeling studies that have been undertaken at a number of places, but the Geophysical Fluid Dynamics Laboratory at Princeton, in America, and Tom Knudsen and some of his collaborators. Basically, the bottom line, as far as what we know from analyzing climate models and the simulations that have been used to understand whether or not we're going to have more storms or less storms, or are we going to have more intense storms, or are we going to have storms that rain more? The answer is that we're going to have a little bit more intense storms, maybe between 1 and 10% intensity increase over the next 50 to 80 years, but they're going to rain more. They're going to rain like 15% more. Okay, that's the prediction from the models, and we're going to have at least the predictions are, and these are still subject to question. This is my view. The prediction is we're going to have fewer storms in total, fewer, but the storms that will get big, will get more intense, we'll have a few more of them. So we're going to have a few more intense storms than we have presently. They're going to rain more, and but we're going to have fewer total number of events. Okay.
And probably also change
But
in the seasons.
if it rains more, then obviously people that live in coastal communities are going to be impacted by more intense rain events. So it makes sense for people to try to prepare for that sort of thing. I had an idea, I know it sounds kind of crazy, but it's a scientific idea, and that is hurricanes are wonderful desalination plants. Yeah, they are. They're fantastic. They evaporate water like crazy, okay, and it's fresh. So if we were smart, we might build a few more reservoirs in certain areas that are prone to this, and we might be able to collect more fresh water. Of course, there's ecological implications, and a lot of people discussing whether or not we should have more reservoirs or not. But anyway, so the seasons, I can't answer that. I don't know. I'm not an expert in that at all. So I would expect, though, that basic results would suggest we're going to get a little bit more rainy storms. They're going to get a little more intense.
The one from last night was very early in the...
Correct. So The discussion now, it's a discussion that's raging, and it's been raging for a while, is whether or not we're going to get, the season is going to be extended. We're going to have earlier storms, we're going to have later storms, perhaps. I mean, it's hard to say based on one event or two events, but it sure seems like this is a pretty early storm, pretty strong. Wasn't anticipated, as I showed. So we have to be prepared for this. Okay? I'm not going to deny that it happens. It's clearly happening. So anyway, okay.
Bon, on va s'arrêter là. Thank you, Mike.
Thank you very much.
Question?
Rien.
Voilà,
Stop.